Hello everybody, I'm Lup from Singapore. Today I shall talk about a fun new way to program NuttX sensors, the visual way. I used to teach adult education classes in IoT. As an IoT educator, I'm always seeking new fun ways to teach about IoT sensors. Here is something I pondered. Can we take some off-the-shelf sensors like the common I2C ones, connect the sensors to NuttX, and send the sensor data to the cloud or a local server without doing much coding? That will be a great way to experiment with IoT sensors with so many interesting possibilities for analyzing and visualizing the sensor data. A sensor network running on NuttX would be so awesome. Maybe we could program NuttX sensors the visual drag and drop way. Let us explore that and how it might send sensor data to the LoRaWAN IoT network encoded with CBOR. Our visual programs could be converted into Zig programs. Zig is a newer programming language that works well with C, and it feels highly suitable for programming NuttX sensors. Our visual program shall also transmit sensor data to the LoRaWAN cloud for easier analysis and visualization. I shall explain in a while. If you would like to download the presentation slides, please head over to this link, lutyuan.github.io/NuttX. That's the letter L, not the digit 1. All my presentations, articles, and source code are available at that link. We have a live demo site that you might want to try out visual sensor programming. This is all client-side JavaScript. We don't capture anything on the server side. Here's a short demo that shows how we do visual programming with NuttX sensors. For today's demo, I shall use the Bosch BME280 sensor, which measures temperature, humidity, and air pressure. Let us watch a quick demo of visual programming with NuttX sensors. We begin by creating a loop that will read our sensor data every 10 seconds. Next, we create 3 variables: temperature, pressure, and humidity. First, we set the temperature. For the value, we select the Bosch BME280 sensor and we read the temperature from the sensor. We clone this twice to set the pressure and humidity. We tweak the BME280 sensor to read pressure and humidity. Our BME280 sensor uses a different path for humidity. We set the path to sensor humi0. Now that we have read the temperature, humidity, and pressure, let us print the values. This is how we print the temperature, humidity, and pressure. We see the code that is being generated as we build our visual program. We are almost ready to transmit the sensor data, but first we create a message variable and we compose the message. Inside the message, we will have 3 fields: T for temperature, P for pressure, and H for humidity. Now that we have composed our message, we shall transmit the message to the LoRaWAN IoT network. Finally, this is the Zig program that is auto-generated for our visual program. When we run this on NuttX, it will read the BME280 sensor and transmit the values to the LoRaWAN network. I shall explain the code in a while. And that is how we do visual programming with NuttX sensors. The demo we saw is made possible by Blockly, which is an open source browser-based toolkit that lets us create visual programs inspired by Scratch. Everything we've seen runs in a web browser, all client-side JavaScript, no server-side code needed. Blockly is customizable with JavaScript. We may create new blocks and support new languages. Blockly doesn't officially support Zig, so we added a code generator to Blockly to support Zig code. And yes, we built the code generator in JavaScript. Maybe someday we'll build it in WebAssembly with Zig, perhaps. Remember this BME 280 block that we drag and drop in our demo? We created as a custom block with Blockly developer tools. Yes, even creating a new block looks just like Blockly programming. We could have programmed our code generator to produce C code, but it would have taken a lot more time and effort. Take a look at this Zig code. It reads a NuttX sensor with a single function. But this is no ordinary function. Sensor barrel here is actually the name of a struct type, and temperature is actually the name of a struct field. Some folks call this meta-programming, and Zig makes it possible because of compile time expressions. This Zig code is super compact, easy to generate. To do this in C, we will have to wrap a C function inside a C macro, which looks really messy. You might be thinking, hey, I'm not familiar with Zig. You know what? I'm new to Zig too. So we'll explain the Zig features in this presentation. Now imagine a classroom of students doing hands-on with NuttX and sensors for the very first time. Temperature sensors, air quality sensors, accelerometers, GPS. What is the quickest way to get them on board? Well, let us create a block for every sensor that's supported by NuttX. Just pick the sensor block, drop it into a visual program. NuttX will handle the plumbing for our students, how to encode data and push the data to the cloud. But will our students understand how NuttX works? That's why we review selective details, like sensor devices are actually located at dev/UOP. So our students will learn this for troubleshooting sensors later. Now this block for the BME 280 sensor generates this Zig code, which looks neat and compact, might be a big plus for learnability. If you're wondering about the try here, well, that's how we handle errors in Zig. Like if we couldn't read the sensor, maybe because the part doesn't exist. This will stop the execution and return the error to the caller, a lot neater than error handling in C. Remember we talked about NuttX doing the plumbing for our students and encoding our sensor the right way? Well, this block does precisely that. It encodes our sensor data in a binary compressed format known as Concise Binary Object Representation, or CBOR. Think JSON, but smaller and more efficient. The message type matters when we're working with IoT devices. Should we encode sensor data as fixed point or floating point? It makes a difference. We shall come back to this. This block encodes a message with 3 fields, T, P, and H, that will be set to temperature, pressure, and humidity. Here is a generated Zig code. This code might look strangely simple. What if we forget a parameter like humidity? What if the parameter is of a wrong type, like maybe humidity is actually a string? With Zig, we can validate this at compile time, so no problems. We shall explain in a while. Compose CBOR will call the tiny CBOR library in C, which shouldn't be a problem because Zig works well with C libraries. Finally, the last step in our NuttX plumbing, sending the data to the LoRaWAN network. LoRaWAN is a low-power, long-range, low-bandwidth wireless network for IoT sensors. By long range, we mean 5 kilometers or 3 miles in urban areas, and up to 15 kilometers or 10 miles in rural areas. But LoRaWAN is also constrained by low bandwidth. We might expect to send 50 bytes in a packet, though to minimize packet loss, we should probably send 10 bytes in a packet. We can send our sensor data to a local LoRaWAN gateway, like ChirpStack, or to a LoRaWAN cloud, like the Things network, which is free to use worldwide, assuming there's coverage in our area. Our sensor data will be aggregated for easier analysis and visualization. This block transmits a message to LoRaWAN, and it will generate this Zig code. Transmit LoRaWAN will call the LoRaWAN library in C. But how did we get the LoRaWAN library? We ported to NuttX, the official reference implementation of the LoRaWAN network stack by Semtech. We are keeping the LoRaWAN stack as is, minimal changes, because the LoRaWAN specification is still evolving. Maybe tomorrow the LoRaWAN stack will introduce a new geographic region, say Antarctica, with its own special LoRaWAN frequencies. Because our LoRaWAN stack is implemented as a NuttX library instead of a NuttX driver, we shall simply merge updates from a reference implementation, and voila! NuttX with LoRaWAN will run in Antarctica. Maybe for penguin sensors or something. Our LoRaWAN library has been tested with ESP32 on NuttX. One final thing before we move on. This every block does something every X seconds. It works great for reading a sensor data and for transmitting the data periodically. Right now we call sleep to wait X seconds in a loop. This might not work for some apps. Later we shall explain why we need proper timers and data logs. Now that we've seen the blocks, let us look at the complete visual program. We have an outer loop that repeats every 10 seconds, which generates this while loop. First thing we do inside the loop, read the temperature from the BME280 sensor and print the temperature. Then we read the pressure from the BME280 sensor and print the pressure. At the right, we see the code that was generated to read the temperature and the pressure. This is how we print the temperature and the pressure in Zig. Next, we read the humidity from the BME280 sensor, which becomes this in Zig. Now we're ready to compose the message. This block composes a message with 3 fields, T, P, and H, that will be set to temperature, pressure, and humidity. This is the Zig code for the block. Finally, we transmit the message over LoRaWAN, which becomes this Zig code. Remember that everything needs to repeat every 10 seconds. We sleep 10 seconds here. And we repeat everything in this while loop that we've seen earlier. This is how an entire visual program gets converted to Zig. We compile the Zig app and link it with NuttX. This is how we generate the Zig library. For details, please check out the presentation, Simpler, Safer, LBGL Touchscreen Apps with Zig and NuttX. We're ready to run our Zig app. Today we run it on the Pinecone BL602 board by Pine64. This is based on Buffalo Lab BL602, which is a RISC-V SoC with Wi-Fi and Bluetooth LE. We connected a Bosch BME280 sensor so we can read the sensor data over I2C. We haven't connected a LoRa radio transceiver, so the C-band encoding and LoRaWAN will be simulated for today. Apologies to the creator of the sensor test demo. We actually hijacked sensor test and replaced the internals with our Zig app. Here we see our Zig app reading the temperature, pressure, and humidity from the BME 280 sensor. Then it composes a CBOR message, simulated for now, and it simulates the sending of the LoRaWAN message. This repeats every 10 seconds. So yep, it's indeed possible to drag and drop a visual program with a NuttX sensor and run it on a real microcontroller with a real sensor. This is a demo of our visual program running on a real NuttX device with a real sensor. Here is our demo setup. We have a Pinecone BL602 RISC-V board connected to a Bosch BME 280 sensor for temperature, humidity, and air pressure. We have compiled the visual program into the NuttX firmware. Pinecone BL602 is now booting our NuttX firmware. Uname says that this is a recent build, NuttX version 10.4.0. Let us check the NuttX devices. Looks normal. These are the sensor devices on NuttX. Barrel 0 is for air pressure and temperature. Humi 0 is for humidity. Both sensor devices are connected to our Bosch BME 280 sensor. Before we run our visual program, let us read the NuttX sensors. Is anyone watching this familiar with sensor test? Let us run sensor test to check that our Bosch BME 280 sensor is working okay. This is how we read the air pressure and temperature. Air pressure is now 1010 millibars. That is close to air pressure at sea level. Temperature is 28 degrees Celsius. Yep, it is warm right now by the Singapore seaside. This is how we read the humidity. Relative humidity is 72%. Yes, it is hot and humid in Singapore. Up till now, we haven't run our visual program yet. But wait, didn't we say earlier that we replaced the internals of sensor test by our Zig program? How were we able to read the NuttX sensors? Well, that is because our Zig program includes the original code of sensor test, all converted to Zig. So sensor test works okay for reading any NuttX sensor, and it will run our visual program too. We can see this from the command line options. Sensor test is now a mix of the old and the new, but 100% Zig. Check out my article on reading NuttX sensor data with Zig. I explain how we converted the entire sensor test demo from C to Zig. Now finally, we run our visual program. The very same visual program that we dragged and dropped in Blockly and converted to Zig. Our visual program reads the temperature, pressure, and humidity from the BME 280 sensor. Yes, the values look correct. Temperature is 28 degrees Celsius. Air pressure is 1010 millibars. Relative humidity is 74%. Then our visual program composes a CBOR message with the sensor data, which is simulated for now. Then it sends the CBOR message to the LoRaWAN network, which is also simulated. This repeats every couple of seconds and runs forever. Once we have integrated the LoRaWAN library, this visual program will transmit sensor data over the LoRaWAN network every few seconds. Yep, the visual program that we created in Blockly runs okay on NuttX. And that was a demo of our visual program in Zig on Pinecone BL602 with Bosch BME 280 sensor. When we implement CBOR encoding and LoRaWAN, we will have a complete IoT app that will transmit sensor data to the LoRaWAN cloud, like the Things Network. With our sensor data in the cloud, we can aggregate the data with Prometheus and visualize the data with Grafana. So many interesting possibilities. Here is a sneak peek of NuttX sending sensor data to the Things Network over LoRaWAN. And this shows how our sensor data will be visualized with Grafana. This works great for multiple devices and multiple sensors. If I ever teach IoT again to a class of students, I would love to see them build an IoT sensor network like this with NuttX devices. Now, our visual program might look overly simplistic though. Real-world applications are actually more sophisticated. For example, it's not okay to send a LoRaWAN message every 10 seconds. Because of the LoRaWAN message limits, we should only send a message every 60 seconds or so, like this second loop here. But if we read the sensor data every 60 seconds, won't the data get stale and outdated? So we should sample the data every few seconds and transmit the average data instead, which means we split our program into two loops. The first loop for sampling sensor data, the second loop for transmitting sensor data. But this won't work. Remember that we use while loops with sleep. The first loop will run forever, and the second loop will never run. We need to fix this with timers and multithreading. When we implement timers and multithreading, we have another problem. How will we pass the sensor data from the first loop into the second loop? Well, we will need to lock the sensor data to prevent concurrent access, right? Maybe use a message queue to synchronize the two loops. In the real world, LoRaWAN messages are also constrained by message size. Depending on data rate and radio interference, we might expect to send 50 bytes in a packet. But to minimize packet loss, it's probably better to send 10 bytes in a packet. So every single byte matters in our sensor data message. One trick is to transmit our sensor data as fixed point instead of floating point numbers. We scale up our numbers by 100 and truncate to integers. This preserves 2 decimal places for our sensor data while transmitting them as integers. Thankfully, Blockly lets us insert math expressions. This is how we scale up our sensor data by 100. Is it really possible to write any kind of program with Blockly? Well, nope. Our code generator for Zig is incomplete. Some blocks won't produce proper Zig code. Assigning a variable twice to the same variable, this won't work because our variables are actually declared as constants. What if we define the variable twice? Once in the outer scope and again in the inner scope inside this loop here. Well, this won't work either. Unique to Zig is a problem of shadow identifiers. Zig won't allow this because the A in the inner loop will shadow the definition of A in the outer loop. It's an odd limitation of Zig. We will have to work around this. In case we are thinking that Blockly is good only for simple toy programs, well, Blockly programs can get quite sophisticated because it lets us define functions. This is how we call a function, passing the value of A as a parameter. And this is how we define a function that adds the values of its parameters. This will generate valid Zig code. it might be useful for, say, computing the average temperature for the last 60 seconds. Remember our BME 280 sensor block and the code that it generates? Let us take a minute to look inside this super function called read sensor. We call it a super function because there's so many sensor things inside it. Like opening a sensor, checking for errors, closing the sensor. Note that we're using the defer statement, which means that the sensor will be closed only when the function returns. By the way, we write underscore equals something when we don't intend to use the return value of the function, like close. Otherwise, the Zig compiler will think that we forgot something and helpfully stop us. Inside our super function, we call iocto to set the standby interval and the batch latency, and then we poll for the sensor data. This should look very familiar to NuttX developers because we call iocto so often. Calling it from Zig looks exactly the same, except that we insert C dot in the beginning. Then we initialize the sensor data struct to zeros and read the sensor data into the struct. And we return the sensor data. Remember earlier we deferred the closing of the sensor? The closing actually happens here when we return from the function. At the top left, there's something interesting going on. Let us zoom in for a closer look. This code allocates a sensor data struct on the stack and fills it with zeros. But what is the type of the sensor data struct? According to our function definition, sensor type is actually a type passed in as a parameter. If we trace back to the function call, we see the name of the struct, sensor barrel, which is passed to our function as a parameter. This means that Zig will happily let us pass the name of a struct type to a function, and Zig compiler will substitute the name of the struct type at compile time. That's why the struct type is declared as comp time. Comp time meaning compile time. You might think, this looks familiar in C, but hold that thought, we got more. The same kind of compile time magic happens when we return a field from the sensor data struct. Field name is the name of a field in the sensor data struct. If we trace back to the function declaration and back to the function call, we see that the field name is temperature. So this code will return the temperature field of the sensor barrel struct. This is so cool. If you're thinking, we can do this in C too. Well, you're right. In C, we will define a C macro with sensor type and field name as macro parameters. In the body of the C macro, we insert the entire code of the read sensor function. So yes, it can be done in C, but it will look really messy and difficult to maintain. Definitely not as elegant as Zig. One final trick for compile time magic. Remember this code for composing a sensor data message? It looks exactly like a C function that accepts a variable number of arguments, right? Well, in Zig, we can process the arguments at compile time. See this comp time assert? This verifies at compile time that we will always have an even number of arguments. So Zig compiler will stop us when we forget a key or a value. This inline while loop is super interesting. Zig compiler expands and unrolls the loop at compile time, which means that we can access every single argument at compile time, like this, like checking whether the argument types are correct. All these features make Zig an easier target for automated code generation, not forgetting type inference, because Zig compiler infers these types, like F32, CBOR message, based on the functions that we call. So we may conveniently drop the types from our generated code. In case you're curious how Blockly generates Zig code, this is the code generator that we wrote in JavaScript that converts this block to this Zig code. Blockly is one huge JavaScript project that might be challenging to maintain. Perhaps in future we might convert the code generator to WebAssembly and Zig for easier maintenance. Here is an interesting idea that Alan shared with me. Imagine Arduino, but in a visual form, with plug and play. It works like this. We plug a sensor into a breadboard, NuttX will recognize the sensor, and the sensor appears in our Blockly program. So if we connect a few sensors, like these, they will all auto-magically appear in Blockly. Now we can program the sensor blocks with some application logic, and we will have an IoT app. That will be a really cool way to get our younger learners interested in IoT sensors. In this presentation, we have covered many topics. Everything that I've covered is explained in these articles, including the source code, visual programming, Zig and Blockly, CBOR encoding, Prometheus, Grafana, and the things that work. If you would like to download the presentation slides, please head over to this link, lapyuan.github.io/NuttX. That's the letter L, not the digit 1. All my presentations, articles, and source code are available at that link. But wait, there's more. LoRaWAN is super complicated, so we need a few articles to cover the LoRa transceiver library, the LoRaWAN library, and how we build a LoRaWAN app with Zig. Now we have a fun visual way to program NuttX sensors and send the sensor data to the cloud. We shall experiment with more NuttX sensors like this interesting all-in-one I2C multi-sensor. There are sensors for light, motion, infrared, ultraviolet, and VOC. That's for volatile organic compounds. Blockly isn't well integrated with the NuttX build process. We might wrap Blockly into a desktop app so that the visual programs generated by Blockly will go directly into the NuttX build. We still have plenty to do, but hopefully someday our IoT students will experiment with IoT sensors the visual NuttX way. Thank you.